Welcome to the class. We are going to see the examples on axial compressor. Before moving to example, let us see the silent features what we learnt from the axial compressor, which are essential to solve the example. First is the velocity triangle. So, this is the velocity triangle for axial compressor, where we have this as C1, this as V1, and then C1 has angle alpha 1, V1 has angle beta 1. So, this is C2 which has angle alpha 2, and then we have V2 which has angle beta 2. Then we have this as U. So, further we would have this small will be CW1, and then this would be CW2, and then this height would be CA. Then we have derived certain relations which include U upon CA is equal to tan of alpha 1 plus tan of beta 1. Further, U upon CA is equal to tan of alpha 2 plus tan of beta 2. We know compressor work is equal to m dot U into CA into tan of alpha 2 minus tan of alpha 1. So, compressor work is equal to m dot U CA into tan of beta 1 minus tan of beta 2. There is a formula which we derived for delta T naught stage, and then this is U CA upon Cp into tan of beta 1 plus tan of beta 1 minus tan of beta 2. So, delta T naught stage is equal to UCA upon Cp into tan of alpha 2 minus tan of alpha 1. Further, if we have the work done factor lambda, then delta T naught stage can be written as lambda 1 lambda dash into U CA divided by Cp into tan of alpha 2 minus tan of alpha. Then we know that there is pressure rise P03 upon P01 is equal to 1 plus compressor efficiency into delta T naught stage. So, this is stage efficiency divided by T naught 1 bracket raised to gamma upon gamma minus 1. So, this is stage efficiency. Further, degree of reaction lambda is equal to Ca upon twice U into tan of beta 1 plus tan of beta 2. So, it is equal to lambda 1 is equal to 1 minus Ca upon twice U tan of alpha 2 plus tan of alpha 1. Free vortex theory says that Cw into R is equal to constant, and as per that theory we have degree of reaction is equal to 1 minus constant divided by R square. So, these are the silent features which we learnt from the topic of axial compressor. So, let us go ahead with the example. The example reads that a 10-stage axial flow compressor provides an overall pressure ratio of 5:1 with an overall isentropic efficiency of 87%. The temperature of air at inlet is 15 degrees Celsius. Work is equally divided between the stages. Compressor has 50% reaction with a blade speed of 210 meter per second and constant axial velocity of 170 meter per second. Estimate blade angles. This is the fact which we have to calculate, where we have to assume the work done factor to be 1. So let us see what is given here. So we have few things which are given in this example. N is 10, which is number of stages. Further, pressure ratio P03 by P01, or what we say as RP, is 5:1. Then overall isentropic efficiency is told as 87%. Inlet initial temperature is told as 15 degrees Celsius, which is 288 Kelvin. Lambda is told as 0.5. Work done factor lambda dash is said as 1. Blade speed U is equal to 210 meter per second and axial velocity CA is 170 meter per second. We know that we are told that work is equally divided between all the stages. If work is equally divided between all the stages, then total change in the total temperature is equal to number of stages into total temperature in a stage. So total temperature stage would be equal in all stages. Since we know if we multiply both sides by Cp, then we can get this Cp into delta T naught as total compressor work, and this is number of stages, and this will become compressor work in a stage. So this total work would get divided equally in all stages. It implicitly means that the temperature rise is same in all the stages. So we can say that temperature rise in one stage is equal to 0.1 into delta T naught, which is total, since there are 10 number of stages. We know the compressor efficiency, so we can find out the total temperature rise. So we know compressor efficiency is equal to delta T naught ideal divided by delta T naught actual. So delta T naught, which is actually we need, which is total, is equal to delta T naught dash divided by compressor efficiency. So delta T naught total is equal to 1 upon compressor efficiency into T naught 2 dash minus T naught 1. We can take T naught 1 common, so T naught 1 divided by compressor efficiency, so T naught 2 dash divided by T naught 1 minus 1. We can use the relation, which is isentropic relation, for the total temperature ratio. So we can have T naught 1 upon compressor efficiency into Rp pressure ratio bracket raised to gamma minus 1 upon gamma minus 1. So here we are using total pressure ratio, which is given as 5:1. So when we keep here T naught 1 is 288, compressor efficiency is said as 0.87, then Rp is 5 and gamma is 1.4 minus 1 divided by 1.4 minus 1. So we get delta T naught total as 193.5 Kelvin. So we can say that delta T naught stage is equal to 0.1 into delta T naught total. So it is equal to 19.35 Kelvin. We can find out delta T naught. We used the delta T naught stage to find out the blade angles, since we are supposed to estimate blade angles. So we have to find out beta 1 and beta 2. So we need two expressions. So first expression we can make use of for delta T naught stage, and that expression says that it is U upon Ca divided by Cp into tan of alpha 2 minus tan of alpha 1. So we can put delta T naught stage, which is 19.35, is equal to U, which is 210, into Ca, which is 170, divided by Cp, which is 1005, into tan of alpha 2 minus tan of alpha 1, and this gives us a relation which says that tan of alpha 2 minus tan of alpha 1 is equal to 0.54472. We name it as equation number 1. Further, we can make use of relation which is for degree of reaction, which is said to be 0.5 is equal to 1 minus Ca divided by twice U into tan of alpha 2 plus tan of alpha 1. So knowing this relation, we can put all the numbers. We can put 0.5 is equal to 1 minus Ca is 170 divided by 2 into 210 into tan of alpha 2 plus tan of alpha 1. So we have tan of alpha 2 plus tan of alpha 1 as 1.2353. We will name it as equation number 2. We can solve these equations simultaneously. We will get alpha 2 is equal to 41.66 degrees and alpha 1 as 19.05 degrees. Since it is a 50% reaction, alpha 2 is equal to beta 1, and beta 1 is 41.66 degrees, and alpha 1 is equal to beta 2, which is 19.05 degree. So this is where we have solved the example which was related to finding out blade angles. We will move to next example, which reads that an axial flow compressor of 50% reaction design has blades with inlet and outlet angles as 45 degree and 10 degree respectively. The compressor is to produce a static pressure ratio of 6:1 with an overall isentropic efficiency of 0.85 when inlet static temperature is 37 degrees Celsius. The blade speed and axial velocity are constant throughout the compressor. Assuming a value of 200 meter per second of blade speed, find number of stages of compressor required if work done factor is unity for all stages. So it is given in the example that we are having lambda, which is degree of reaction, as 0.5. We are told that inlet and outlet blade angles, so beta 1 is 45 degree and beta 2 is 10 degree. We are told that the overall pressure ratio is RP pressure ratio or RC, RP or RC pressure ratio is 6:1 and isentropic efficiency is 0.85. T1 is 37 degrees Celsius, which is equal to 310 Kelvin. We are told that U is equal to 200 meter per second and lambda dash is 1, which is work done factor. So we have to find out in this example the number of stages required. So here, as what we did, we know that total temperature change in the compressor is equal to number of stages into total temperature change in a stage. If we divide, every stage is having same temperature rise. So for that, we can find out the overall temperature change or total temperature change in the complete compressor as 1 upon compressor efficiency into T01 into RC, which is compression ratio, bracket raised to gamma minus 1 upon gamma minus 1. So knowing this, we can put delta T naught total is equal to 1 upon compressor efficiency, which is 0.85, total temperature is 310, compression ratio is 6, 1.4 minus 1 divided by 1.4 minus 1. So we get total temperature change in the complete compressor is 244.12 Kelvin. Now we can find out the stage temperature rise, delta T naught stage, and this is equal to U into Ca divided by Cp into tan of beta 1 minus tan of beta 2, since we are given with beta 1 and beta 2. So we can put this over here and we can get that delta T naught stage is equal to U is told to us, which is 200. So we are having U as 200 into Ca divided by Cp as 1500, tan beta 1 is 45, so tan is 1, tan beta 2 is 0.1763. we will put as equation number 1. We know that U upon Ca is equal to tan of beta 1 plus tan of beta 2. So that is equal to 1.1763. So we know U is equal to 200. So Ca is equal to U divided by 1763. So Ca becomes 170.02 meter per second. Now we can put this Ca in this equation number 1 and we can get delta T naught stage as 27.86 Kelvin. So this is the temperature rise in the stage, and this temperature rise in the stage is required for us for the calculation of total number of stages. Having said this, here we are making use of the fact that alpha 2 is equal to beta 1 and alpha 1 is equal to beta 2, since we are told that we are having degree of reaction as 0.5. So we can know that total number of stages is delta T naught total divided by delta T naught stage. So we have 244.12 divided by 27.86, and hence the answer comes around 9. So we need 9 stages for doing this compression work. Let us go to the next example, which says that find the polytropic efficiency of an axial compressor from the following data. The rotor and stator blades are symmetrical. So the rotor and stator blades are symmetrical. This statement itself means that we are given with degree of reaction 0.5. So we can take alpha 2 is equal to beta 1 and beta 2 is equal to alpha 1. Mean blade speed and axial velocity remains constant throughout the compressor. Assuming a value of 220 meter per second of blade speed and the work done factor to be 0.86, find the number of stages required. Also find the inlet Mach number relative to the mean blade height of the stage. Assume R to be 284.6. And given data is total head inlet pressure ratio is 4, overall head isentropic efficiency is 85%, total head inlet temperature is 290 Kelvin, inlet air angle for the rotor is 10 degree, outlet air angle for the rotor is 45 degree. So first we have to find out polytropic efficiency. So we don't have to write the given things for finding out polytropic efficiency, since we can use the formula what we already know. Compressor efficiency is T02 dash minus T01 divided by T02 minus T01. So we can take T01 common, so T02 dash divided by T01 minus 1 divided by T02 upon T01 minus 1. So here we can make it in terms of compression ratio or pressure ratio. So we can write RC bracket raised to gamma minus 1 upon gamma minus 1. We will mention it as pressure ratio, which are same. So pressure ratio of the compressor. So this is bracket raised to gamma minus 1 upon gamma, since it is isentropic, and in the bottom we have polytropic process, so it is n minus 1 upon n minus 1. But we know that we can represent the denominator in terms of polytropic efficiency, so we can have Rp bracket raised to gamma minus 1 upon gamma minus 1. We can say in the denominator it is 1 upon compressor's polytropic efficiency into gamma minus 1 upon gamma minus 1. Now we can put whatever it is known to us. Pressure ratio is 4 bracket raised to 1.4 minus 1 divided by 1.4 minus 1, and here also it is 4 raised to compressor's polytropic efficiency into 1.4 minus 1 divided by 1.4 minus 1 equal to 0.85. Here in this case we just don't know what is compressor's polytropic efficiency, and this comes out to be 87.58%. So this is what we can get from the given data, which is just the pressure ratio, overall pressure ratio, and the compressor's isentropic efficiency. We can make use of the given quantities for rest of the things. So given is here, we are told that blades are symmetrical, so we are told that lambda is equal to 0.5. We are told that alpha 1 air angle at the inlet is 10 degree. So alpha 1 is equal to beta 2 is equal to 10 degree, and alpha 2 is equal to beta 1 is equal to 45 degree. U is told as 220 meter per second. T01 is 290 Kelvin. Then as it is known, Rp compressor is told as 4, and work done factor lambda dash or lambda 1 is given as 0.86. So we are supposed to find out number of stages or relative Mach number at the inlet. So again for number of stages we can find out delta T naught total using the formula for isentropic efficiency, which says that T01 total is equal to T01 divided by compressor efficiency into Rp compressor bracket raised to gamma minus 1 upon gamma minus 1. So we have T01, which is told as 290 divided by 0.85 bracket raised to 4 into 4 raised to 0.286, which is known to us minus 1. So this gives us total temperature change in the complete compressor as 166.01 Kelvin. For stage total temperature change, we can use the formula of beta, which says that UCA upon Cp into tan of beta 1 minus tan of beta 2 into work done factor. But before that, we have to find out Ca, since Ca is required in this formula. So we can only U is given, so Ca can be found out from degree of reaction, which is given as lambda is equal to Ca upon twice U into tan of beta 1 plus tan of beta 2. So we can get it as Ca upon 2 into 220 into tan of beta 1 is 0.1763 plus beta 1 is 1. Tan beta 1 is 1 and tan beta 2 is 0.1763. This is equal to 0.5, and this gives us Ca, which is 187.02 meter per second. Now we know Ca, we can find out delta T naught stage, and delta T naught stage turns out to be 220 into 187.02 divided by 1005 into tan of beta 1, which is 1 minus 0.1763 into 0.86. So we have delta T naught stage is equal to 29 Kelvin. So we can find out number of stages as 166.01 divided by 29, and we get around 5.72. so it is around 6 stages required. Then we are supposed to find the relative Mach number, and relative Mach number can be found out using relative velocity, but for that we have to first find out relative velocity from velocity triangle. V1 is equal to Ca upon cos of beta 1, so which is equal to 264.5 meters per second. Then we need to know the formula, which is relative Mach number 1 is V1 upon under root gamma R T1. So now V1 is known, we just don't know T1 since we are known with T01. So we can find out T1 from T01 using the formula, which says that T01 is equal to T1 plus C1 square upon twice Cp. But we again don't know C1, so C1 can be replaced again by Ca by saying that C1 is equal to Ca upon cos alpha 1 bracket square divided by 2 Cp. So this gives C1, and then we can find out T1 from here from known T01. So we get T1 as 272.8 1.03 Kelvin. So we can know Mach number relative at inlet is equal to V1 upon under root gamma RT1, and then this is equal to 264.5 divided by 1.4 into 287 into 272.03, and this gives us MR1 as 0.8. So this is how we would have solved the example for the axial compressor, where we were asked to first find out the polytropic efficiency and then the Mach number and also number of stages. We will move on to next example, which states that air at a temperature of 290 Kelvin enters a 10 stage axial compressor at the rate of 3 kg per second. The pressure ratio is 6.5 and isentropic efficiency is 90%. The compression process being adiabatic. The compressor has symmetrical blades. Axial velocity is 110 meter per second and it is uniform across the stage, and mean blade speed of each stage is 180 meter per second. Determine the direction of air at entry 2 and exit from the rotor and the rotor blades, and also power given to air, given that assume Cp as 1.005 and gamma as 1.4. So let us see what is given. In this example given, first is T01, which is 290 Kelvin, number of stages 10, then m dot is 3 kg per second, then Rp compressor as 6.5, then compressor's isentropic efficiency as 90% or 0.9, blades are symmetric, so lambda is equal to 0.5, then axial velocity Ca is equal to 110 meter per second, and then mean blade speed U is equal to 180 meter per second, and then we are supposed to find out the exit and entry rotor and stator angles and power input given. So we can find out first total temperature rise, which is equal to T01 upon compressor efficiency into pressure ratio of compressor bracket raised to gamma minus 1 upon gamma minus 1. So we can know the overall total temperature rise as 290 divided by 0.9, which is compressor efficiency, into 6.5 bracket raised to 0.286 minus 1, and this gives us total temperature change in the complete compressor is 228.14 Kelvin. So since there are 10 stages, so delta T naught stage is equal to 22.814 Kelvin. But we know that delta T naught stage is equal to U by Ca upon Cp into tan of beta 1 minus tan of beta 2. So here we know that 22.814 is equal to 180 into 180 is U, Ca is 110 divided by Cp 1005 into tan of beta 1 minus tan of beta 2. So we can get tan of beta 1 minus tan of beta 2 is equal to 1.0 157, and we will say it as equation number 1. We can know other equation from degree of reaction, which is Ca upon twice U into tan of beta 1 plus tan of beta 2. But degree of reaction is half, and half is equal to Ca 110 divided by 2 into 180 into tan of beta 1 plus tan of beta 2. So we get other expression as tan of beta 1 plus tan of beta 2 is equal to 1.6363. So this we will say it as equation number 2. We can solve the equation simultaneously. We will get tan beta 1 is equal to 1.39, which gives us beta 1 is equal to 54.4 degree, which is also is equal to alpha 2, and tan beta 2 is equal to 0.239, which gives beta 2 is equal to 13.45 degrees. Now we can find out compressor work. It is told to us m dot into U into Ca into tan of beta 1 minus tan of beta 2. So we have tan of beta 1, we have now tan of beta 2. We can put everything. So m dot is also given 3, U is 180, Ca is 110, tan beta 1 is 1.39, tan beta 2 is 0.239, and this gives us compressor work as 68.779 kilowatt, and this is obtained from the velocity triangle. So this is per stage. This is for one stage of the compressor. Since there are no total 10 stages, so it is 10 into stage work. So it is 687.79 kilowatt. So this is how we have solved the other example given on the compressor. Having said this, we will see the other examples and other concepts in the other classes. Thank you.